This first video for Module 15 looks at physical and chemical weathering. Well, up to this point, our focus on the lithosphere has looked at the internal processes, or processes that create new landscapes. And we've talked about plate tectonics and volcanic action, so things that make new places. From this point in the course until the end, we're going to be looking at the other side, and those are the external processes, or processes that tear down existing landscapes. And those include weathering, mass wasting, and erosion. So we focus here on weathering. What is weathering? What exactly is weathering? Well, we can say it's the disintegration and decomposition that destroys the coherence of bedrock, that breaks big rocks up into smaller rocks, if you will. And we see in the bottom view here the disintegration of lots and lots of big rocks into smaller rocks. And we can say that the atmosphere is a key agent in weathering. So we'll talk about some ways that the atmosphere makes contact with rock. So let's walk through that list. How does the atmosphere come in contact with rock? We can say that microscopic open spaces provide one way for air to make contact with rock. So here's an example of granite. Even granite that seems pretty solid and pretty dense has these microscopic open spaces. We've spoken previously about faults. So faults are another way that the atmosphere can find its way into rock, and joints, where you might not necessarily have displacement of rock, but just a crack or a fracture in rock. There are also lava vesicles, where tiny bits of lava, perhaps in the form of veins, has pushed its way through rock and provided an opening. In solution cavities, we haven't really spoken too much about the effect of chemical weathering and opening up passageways like this large solution cavity, but we'll look at that in a subsequent video. So what are some ways that rocks weather? Well, let's take a look at just some examples. Block disintegration is one, where you see the rounded edges of this rock is beginning to form as fracts and joints begin to break it up into smaller pieces. Another is abrasion, just where rocks are bumping into each other. We see that at the beach. We see some beach waves off in the distance here coming in, and or in rivers. So river rock would be an example of where this abrasion takes place, just rocks bouncing and bouncing into each other. This type of weathering, where spheres will weather, where rocks will sort of weather like like almost like an onion, is another example, and we'll talk about this in a little bit greater detail here in a minute. Something called slaking, where moisture gets into rocks and causes it to expand, in the case of clay, is another. So one thing to consider is the surface area of rock exposed. Surface area has a lot to do with the speed at which a rock will weather. And basically the rule is the more contact that the atmosphere has with rock, the greater speed at which weathering takes place. So here we have the surface area of this, let's just say it's a box, it's 12 by 12. It has a surface area of about 864 square inches. So if we break this thing up into smaller pieces, we kind of subdivide it into smaller pieces, we can increase its surface area considerably and increase opportunities for weathering to take place. So as big rocks are broken up into smaller rocks, this whole process accelerates, and you can sort of imagine that as surface area increases. How about some types of weathering? Well, we're going to talk about two basic types of weathering. Mechanical weathering is weathering that does not involve a chemical change in the rock. So so you might liken it to taking a rock hammer and smashing a rock and breaking it up into smaller pieces. And then chemical weathering is where we do have a chemical reaction that helps to break up rocks. So we'll look at we'll look at both of these separately and then a little bit together. Okay, we'll start with mechanical weathering. So this is the physical disintegration of rock without a change in its chemical composition. So what are some examples of mechanical weathering? Well, one of the most powerful forces in physical or mechanical weathering is water. So when water finds its way into cracks and joints during the day, the water may be in a liquid form. It may freeze at nighttime, and when it freezes, one of the properties of water when it freezes into ice that we know about is that it expands. That water will expand when it becomes ice, and it will effectively push those cracks and joints deeper into the rock. And here's an example of here's another example of frost wedging that you can see in this rightmost photo. And frost wedging on the landscape isn't really hard to find. As I mentioned here, it's also called frost shattering. So here's another example of a rock that's been affected in this way. And this process is just repeated day after day after day, every single night where temperatures drop below freezing. We'll see this frost wedging take place. Some other examples of frost wedging that are sort of interesting. Needle ice is where water drawn upward by capillary action freezes, and this may push soil particles out of the way, as in this image. So these tiny needle-like things are formed in soil. There's also something called frost heave, where the soil is actually lifted when the water freezes and pushed up out of the way. So you see here particles or little clumps of soil that have been pushed out of the way by freezing water down inside that soil. We know that these types of things can be very damaging to things that human beings build, like sidewalks. This is an asphalt sidewalk that has major cracks in it because of the damage caused by water. So water got below the sidewalk and pushed upward, forming those cracks. And then when water gets into the cracks, the process may accelerate even more in terms of breaking up the sidewalk. A second way, or a second example of mechanical weathering, is salt wedging. Salt wedging is where water that seeps through rock may have a small amount of salt dissolved in it, and when that water emerges at the edge of a rock, that salt is left behind, and as those salt crystals form, they may actually help to break up the rock. Let me show you a better example. We have two examples here in the photos of salt crystal formation. And here's one on granite steps. So even really tough rocks like granite can be affected. But here's my personal favorite example. In this example right here, you see sort of an Anasazi settlement. So this is a settlement that's pretty big, where people lived at one time, the ancient ones, the Anasazi, and they would build their homes in places like Arizona and New Mexico in these notches in the side of a cliff. So you see this notch that I'm pointing at right here in the side of the cliff at the base of sandstone. And that sandstone may be sitting right on top of impermeable shale, meaning shale or very, very dense rock that water has a hard time soaking into. So here's what happened. You have rain that finds its way and sort of moves through this permeable sandstone, and it hits that impermeable layer of shale, and it moves horizontally and emerges where this notch is. And when it emerges, salt crystals will form, and as those salt crystals form, they'll break up a tiny bit of rock, forming the notch. Some other ways that this mechanical weathering can take place is through what's called thermal pressure biological weathering. So those are really kind of different things. Let me kind of illustrate what's happening in this example. Thermal or pressure weathering is represented by this rock, which, similar to the earlier rock that I pointed out, sort of breaks up like kind of like the skin on an onion. And here's how it does it. Imagine that when granite forms, granite is a intrusive igneous rock that forms where molten magma hardens underground. So imagine when magma hardens into granite underground, it's under a lot of pressure. So it's confining pressure coming from every direction. It's also perhaps pushing outward a little bit. So here we have outward pressure shown by these vectors, and then also a confining pressure from rock that's around the granite. Then imagine, we've got our dinosaur running here, imagine later when the land surface is lowered, now that rock no longer has the confining pressure pushing down on it from above, but it still has that pressure from inside pushing outward, and we get what's called unloading and exfoliation. So it's exfoliation like your skin exfoliates, same idea, and it produces things like this. These giant slabs of granite have broken off from the main slab of granite as that pressure has been released. So we call this whole process exfoliation, and it's part of this unloading process that granite will go through. Biological weathering is where plant roots and other biological activities can help break up rocks. So here's one example of a pine tree growing and splitting a rock. And another example, this looks like I always think of Lara Croft Tomb Raider when I think of this trip that I took to Cambodia some years ago. But those are roots that have surrounded a pretty ancient temple site. Other examples of biological weathering include lichens, where lichens help to break up a rock. Lichen is sort of a combination, sort of a community of bacteria and fungi living together in rock, and the lichen are using some rocks that are some of the rock as a way of developing and creating food. All right, so look at this picture here. This is actually what's now a national park in the southern part of Colorado. This is Black Canyon, the Gunnison National Park. It used to be a national monument for a long time, but if you look at the two slopes, try to come up with a theory as to why they're different. Here we have the same type of rock on both sides of the river. Here we have the Gunnison River running in the bottom of the view. We have the same type of rock on each slope, but one of the slopes is much steeper than the other, and the other slope that's not so steep looks like it has a lot of weathering has broken up rock on that slope, and there's even trees growing on that slope. So any theory as to why? Well, it has to do with angle and aspect. So it has to do with this angle relative to the sun and the compass direction, or the azimuth, that this faces. This is a south-facing slope, the gentler slope here, that's getting a lot more sunlight during the day, and there's a much faster rate of weathering happening on this slope as a result through that freezing and thawing action that we talked about a little bit previously. So this is mechanical weathering, an example of extreme mechanical weathering over on the right-hand view, and a much slower process of mechanical weathering in the right and on the left-hand side of the photo. Okay, let's turn our attention to chemical weathering. So we know chemical weathering involves the disintegration of rock that's caused by chemical reactions. So there's water, but other substances that might be dissolved in the water. So let's talk about some of those. This example of chemical weathering, we see a change in the rock surface. Perhaps you've taken a rock hammer, you've smashed it against a rock, or you've broken up a rock in another way, and you might notice that the color of the rock where you've exposed fresh rock to the air is a different color from the rest of the rock. That's because the outside of the rock, before you smashed it, was affected in a significant way by atmospheric chemical weathering. So what are some types of chemical weathering? Well, let's walk through a little laundry list here. We'll talk about where oxygen interacts with rock as part of oxidation. So oxidation is essentially another way of saying rust. The rock is rusting, and that's where you have rock that has a high amount of iron in the rock material that interacts with oxygen and creates a softer, more easily eroded material. So the reactant here is oxygen interacting with rock and causing and creating sort of a byproduct that's softer and more easily eroded. And you know this if you've ever been in a car accident. So you know that you need to get your fender fixed or the side of your car fixed, because if you don't, it's eventually going to rust. And if you really leave it and don't do anything about it, it may rust all the way through, and you'll be really sorry. So oxidation happens very frequently to various types of metals, like this wagon wheel. That's one example of a type of rock that is susceptible to oxidation. Well, let's move on and talk about our next reactant is water itself. So where water interacts with rocks, in the case of, as shown in this view on the right, these are feldspars that produce clay minerals as sort of as a byproduct, but where water interacts with the rock, we call it hydrolysis, again, producing something softer and more easily eroded. And this hydrolysis is something that really affects volcanic rocks. So in places like Hawaii or anywhere with a lot of volcanic soils and volcanic rock, hydrolysis is a huge contributor to chemical erosion. Perhaps you've seen this scene in some movies. This is not far from where I grew up, outside of LA area. These are the Alabama Hills, and these are granite rocks that have been sculpted by hydrolysis. And this is a really famous place for filming a lot of movies. It looked like it was sort of representative of some of the U.S. West. So a lot of particularly films that were made in the 1940s and 1950s were filmed here at the Alabama Hills. But an example of hydrolysis that has helped to shape granite. The next type of reactant I want to mention is carbon dioxide. So we know carbon dioxide, when it comes into contact with rocks, principally rocks like limestone, can remove that limestone. Where carbon dioxide is mixed with water, you get a weak acid, like acid rain, and that weak acid will remove rock and carry it away. So this is an example of some limestone that's been carved or sculpted by carbonation, and a larger area where these deep fissures called grikes have been created in the same way. So the slabs in this scene are called clints, and the deep sort of kind of fissures that have been opened up by carbonation are called grikes. Some types of things that people create are also affected by carbonation, like the statue that's been severely disfigured by in this case, acid rain. Basically the same process. I call this statue repair. And sometimes you'll see gravestones affected in a similar way by carbonation, so they're unreadable, or even, mostly gone, as in the case of this gravestone. Living things can also break up rock in a surprising way, and we've talked already about lichen, but here we have starfish, and here we have the bottom of a pier that's covered with barnacles. So living things can also accelerate the process of mechanical or of chemical erosion. And then here's some gravestones that have been affected by chemical erosion or chemical weathering. And you can see that some of them are just really hard to read. So we have 1870, where the definition of what's carved on that is there's really not much left to make it readable. An engineering department at a university came up with this idea of having a stone wall that just lays out exposed all the time, and the rocks are basically exposed to the same elements in the atmosphere that lead to chemical erosion happening at different rates, and they can come back occasionally and look at what's happening with some of the various types of rocks in the wall to see which ones are eroding a little bit faster. We can actually see this rate of chemical weathering as it affects gravestones, and I just put this graph up here that sort of shows the number of years, so time in years, and the surface reduction in millimeters that happens. It's a pretty constant rate at which material is removed by carbonation and other kinds of chemical weathering, affecting this type of gravestone and making them unreadable. All right, I mentioned I was going to sort of put it all together, and this I've created this diagram so you can see sort of the relationship between a couple things. On the axis that sort of runs up and down, we've got temperature, hot or cold, if you will. So we have colder temperatures up near the top, warmer temperatures near the bottom, and then along the bottom here we have an axis that represents moisture or annual rainfall or snowfall, wet to dry, and this shows the type of weathering that would be most effective. So we see where it's wet and hot, like in places like rainforest areas, we see strong chemical weathering. Where it's a little bit drier but still fairly warm, moderate chemical, and where it's very, very dry but hot, minimal weathering of any kind. So on the other axis, you'll see where temperatures are sort of in the moderate to cold sort of zone, we see mechanical weathering being more of an effect, or having more of an effect in terms of breaking up rocks. So here we have moderate and strong mechanical weathering happening in colder temperatures with some amounts of moisture. And I've sort of represented the same idea here in stretching our view across different latitudes. So if we're trying to imagine, what parts of the world are most affected by either chemical or mechanical weathering, and again, equatorial areas, areas in the tropics like tropical rainforest areas are very much affected by chemical weathering. And this is sort of the relative depth of how far down into the rock you might see chemical weathering affect rock. So deeper, much deeper, when you're talking about equatorial areas, tropical rainforest areas. In the arid desert, we see the blue area, mostly mechanical weathering taking place, not much chemical weathering. It's just too dry for chemical weathering to take place. Then when you get into sort of mid-latitudes, some amount of chemical weathering, some amount of mechanical weathering as well. And then up in the very high latitudes, up in the polar regions, a little bit of mechanical weathering, not a lot of chemical weathering. It's just, again, it's probably too cold up in those areas and also dry.